Starting where we left off last time, I said that only delta z and delta m squared will contribute to the propagator, to the corrections to the propagator, whereas delta lambda will appear as a 4-valent vertex contribution. Expanding e to the minus s, the additional contributions that we will get to the propagator from delta z and delta m squared will be minus k squared delta z and minus delta m squared. Let me also tell you why. So the reason is that we expand e to the minus s, and then some other contributions will arise, but it is probably more intuitive if I explain this in the following manner. So the following explanation is not reported in David Skinner's notes. So what you will find in David Skinner's notes, you will find that the considerations that we are basically doing in this lecture and also in the previous one, well, these considerations are also reported in Skinner's notes. Anyway, maybe a more intuitive way to explain this kind of contributions to the propagator is the following, in my opinion. So you have 1 over k squared plus m squared, which is the so-called quote-unquote classical propagator. So this is just the contribution to the propagator that you have without any interactions, and this is the result that you get, right? And it is also what we found in the previous lectures, not just the previous one, but also the ones that came before, and those lectures are not contained in David Skinner's notes. So as you can see, sometimes you find stuff that's also contained in David Skinner's notes, but other times what I'm trying to do is I'm trying to give more insights. But anyway, if we consider the terms delta z and delta m squared, this classical propagator will be something like this: 1 over 1 plus delta z times k squared, due to this contribution here, delta z. If you think about it, this 1 multiplied by k squared appeared because in the action, in the initial action, so this is the action containing the counter terms. But in the action that we started from, which was this one, s sub lambda 0 phi, we had this term without delta z, so we had 1/2 d phi squared. So when you consider the Fourier domain and you transform this term and you find the propagator, what you find is that basically you have this k squared in the denominator. So with this delta z correction, you simply have 1 plus delta z. It's quite easy to understand. And then instead of m squared, what you get is m squared plus delta m squared, like this. So this is how the propagator changes, because we have changed these constants m squared and the constant that multiplies k squared. Now if we expand this term with respect to delta m squared and delta z to first order, this will become, well, we are considering delta z and delta m squared as small terms, so it's an expansion. We will see that the word small is quite a confusing one, or dangerous, quote-unquote dangerous, because it's not totally true that delta m squared and delta z are small terms, and this will be more apparent later, but still we can expand this function in powers of delta z and delta m squared. So we are thinking that delta z and delta m squared are small now, but only for convenience. In any case, you can expand this function near the point delta z equal to 0 and delta m squared equal to 0, by assuming that delta z is much smaller than 1 and delta m squared is much smaller than m squared. Anyway, what you have here is 1 over k squared plus m squared, and then you have minus 1 over k squared plus m squared. squared, and then here you have k squared delta z plus delta m squared. Now you can see here that we have this minus sign together with k squared delta z and also minus delta m squared. Whereas this factor that we have in front, if you remember when we found the corrections to the propagator, we also had such a term that multiplied an integral of the following kind. We had something like minus lambda over 2 integral d4p over 2 pi to the fourth 1 over p squared plus m squared. So basically this multiplied this term. So you can see that we have some other contributions that are given by minus k squared delta z minus delta m squared. And if you recall, we defined this to be capital pi of k squared. So capital pi of k squared, or more specifically, its one loop contributions are this. So we have added these terms to this function. And we calculated this integral in the previous video, so I can simply recall the expression. So let me write it here, capital pi of k squared equal to, let me write minus k squared delta z first, minus delta m squared, and then we have this integral that we computed, and in particular it was equal to minus lambda over 32 pi squared, and then we have lambda 0 squared. So if you recall, we had to integrate over mod p smaller than or equal to lambda 0. Because the energy scale of our theory was lambda 0, then we have minus m squared natural log of 1 plus lambda 0 squared over m squared, like this. So if you recall, this term was divergent. It is divergent because as soon as we let lambda 0 go to infinity, this term goes to infinity, it grows to infinity, and therefore we have divergent results. Now, the advantage of having delta m squared and delta z is to correct these divergences. So this is the renormalization process, or renormalization procedure, if you want. Now, if you recall, we also had the propagator delta of k squared. This is the notation that we used the last time, and this was equal to 1 over k squared plus m squared minus capital pi of k squared. So this is the exact propagator. So you have this additional contribution to the denominator that we derived in the previous video. And we want to require that the propagator, this propagator here, has a simple pole when k squared is equal to minus m0 squared. Namely, m0 is the experimentally measured mass. So that's why I'm calling it m0 squared. We know in general that the propagator, when we set k squared equal to minus m squared, for example, if we didn't have any interaction in our theory, this m0 would be exactly m, and this m would be coincident with m, and therefore the propagator has an infinity, a divergence at k squared equal to minus m squared. But if you have contributions due to interactions and in higher order terms, higher loops, and so on, in general, instead of m squared, we can define m0 squared. So it is a contribution given by the experimentally measured mass. So because all these interactions are going to change the experimentally measured mass. But we still require that the propagator has a simple pole when k squared is equal to minus m0 squared. So it is quite intuitive. Therefore, here we require that minus m0 squared plus m squared minus capital pi of minus m0 squared is equal to 0. And we define this to be condition 1, and I will denote it like this. Now, since the pole is simple, we can also calculate the residue. So you have to know what residues are. So you have to have some knowledge of complex calculus in this case. If I want to calculate the residue of delta of k squared, at the point k squared equal to minus m0 squared? Well, it is quite simple to calculate the residue if the pole is a simple pole. So in particular, it means that we have to take the limit as k squared goes to minus m0 squared of, we multiply this function here by k squared plus m0 squared, and we divide by k squared plus m squared minus pi of k squared, right? Now, since we are near the point k squared equal to minus m0 squared, this term here will give us something like m0 squared, very close to m0 squared, something very close to m0 squared because of condition 1. So you can see that when we set k squared equal to minus m0 squared, we have this equation. So pi of minus m0 squared is equal to basically minus m0 squared plus m squared. But this means that this denominator here can also be written as something like k squared plus m0 squared. And therefore we expect that this limit will give us 1. And this turns out to be another condition that we have to impose on pi. In particular, if you rewrite this limit by using the L'Hopital rule, you can take the derivative of the numerator with respect to k squared and also the derivative of the denominator with respect to k squared, because as you let k squared go to minus m0 squared, you get 0 divided by 0, so it's an indeterminate form, and therefore that limit can also be rewritten in the following way. So the limit as k squared goes to minus m0 squared, you have 1 divided by 1 minus the derivative of pi with respect to k squared, and of course we have to take this derivative and then we let k squared go to minus m0 squared. We know that the result here should be 1. Therefore, it means that this derivative here should be 0. So we get another condition on the function capital pi. So the derivative of capital pi with respect to k squared at k squared equal to minus m0 squared, this should be 0. And this is what we call condition 2. Now, if we set up our theory so that m is equal to m0, condition that we called condition 1 will simply become capital pi of minus m0 squared equal to 0. So we are assuming now that m, the mass that we call m, in our theory is the experimentally measured mass. And therefore here you get 0 from this because we have set m equal to m0, and therefore the condition that we obtain, the simplified condition, is this one. Now condition 2, this condition here, is very simple. It gives us a very simple result. If you apply that to this function here, when you take the derivative of capital pi with respect to k squared from this function here, you get minus delta z, right? So this condition simply tells us that delta z should be 0. We set delta z equal to 0. And condition 2, which is this one, gives us the following. So in particular, you simply have to remember this expression. We know that now we have set delta z equal to 0, so you don't have that term anymore. And remember that we have chosen our theory in such a way that m is equal to m0, so it is the observed mass here and here. And therefore we get an equation that will allow us to find delta m squared. So delta m squared will be minus lambda divided by 32 pi squared lambda 0 squared minus m0 squared, or just m squared, natural log of 1 plus lambda 0 squared divided by m squared. And this is the equation for delta m squared. So you can see that delta m squared, this correction to the mass, depends on this scale, lambda 0 squared. At this point, we realize that this delta m squared, as soon as we let lambda 0 go to infinity, we see that it contains a divergence, because this term here will give us something that goes to infinity as lambda 0 grows larger and larger. And remember where we started from. We started from this expression here, pi of k squared, and we wanted to make sure that this pi of k squared, which is just a correction to the propagator, is something that does not go to infinity. In particular, in this specific case, we saw that this is a constant and it should be equal to 0, because this part here does not depend on k, and that since delta z is equal to 0, we see that pi of k squared should be a constant, because it does not depend on k for this specific case. At least, we are considering only one loop contributions. If we computed the path integral to higher order in perturbation theory, including the contribution of higher loop Feynman diagrams, well, we would have to make further tunings to the parameters delta m squared and delta z, proportional to higher powers of decoupling lambda, in order to retain a finite result.